Today we begin a new topic, quite different from the previous ones. And so let's see what it is. So it's about the way that an electromagnetic wave propagating, so crossing a region which is filled up with some plasma, can be affected. And we will see that there are different effects that contribute to change the properties of the electromagnetic wave. So we will go through this from a purely theoretical point of view with a lot of examples. And then in the end, particularly in the end, not today, because I wouldn't be, it's going to take us a few classes. In the end, I will mention one of the applications, one of the astrophysical themes, which are, to understand which, you really need to understand all the physics that we are going to see today and in a couple of days. So what is the context? Well, the context is that very often in several astrophysics contexts and environments, essentially the electromagnetic wave, due to any possible source that you can think of, in the path when traveling from the source to the observer, which is in this case it's us ourselves, it doesn't cross completely vacuum. So at some point it has to cross some regions which are filled with plasma because possibly, of course, so ionized gas essentially, which can be in different environments. So for example, within our own galaxy, so between different stars, of course, there are the so-called interstellar gas, which in many cases can be ionized to some level. So a region with plasma, or just between different galaxies. So if you imagine to observe, and indeed that's going to be an example that we will make in the end, a region, so a source which is extragalactic, so belonging to another galaxy. So the region between the different galaxies, so the intergalactic medium, is not completely empty. There is a typical gas with a typical density of 1 particle per cubic meter, if I remember correctly, depending on it. So the density is extremely low, but you have to consider that the path which is traveled by the wave, by the electromagnetic wave, is very long, can be of the order of several hundred megaparsec, if not gigaparsecs. So even if the density is extremely low, the cumulative effect can be measurable, and indeed it is. This is just to prove you the possibility that an electromagnetic wave due to a source you are interested in is affected by the plasma, which has to be crossed along the line of sight, is nothing but rare, is very common. So it's important to understand how the electromagnetic wave is affected just by this. First of all, well, to understand the physics of this is important. Why? Because if you want to study the properties of the source responsible for the electromagnetic wave, you have to be able to disentangle, to separate the properties which are intrinsic to the source from those which are just due to the region of plasma which the electromagnetic wave has crossed, and which have nothing to do, of course, with the source itself, just because it's along the line of sight. And we will make a few examples, particularly in our own galaxy, because our own galaxy is filled up with a lot of electrons. So plasmas. We will see also the effect of magnetic field. And sorry, the very last thing I will be talking about, I will be briefly mention a very hot topic in the current research in astrophysics, which is our so-called fast radio bursts, which is something which is being discovered a few years ago and which has been attracting a lot of interest, and which is also which will be one of the main topics of my optional course on multi-messenger astrophysics. So this is just a starter. So let's let's start seeing what is the physics behind this interaction. So essentially, let's start with the easiest possible wave we can think of. So a plane wave, and in particular, we will consider different kinds of polarization of the wave. So in particular, let's think for just a linearly polarized wave. So this is the scheme we already adopted at the beginning of the course. We know the property. I still remind you, we are in the Gaussian system. So with all the benefits, with this unit, so both electric and magnetic field have the same magnitude, and they work like this. So this is just the equation, which is solution of the Maxwell equation in vacuum. So we will focus on the effect on the electron, and in particular, how the resulting electromagnetic field is affected by the response of the electron to this wave. We will not consider, as I wrote here, the effect of ions, although they indeed are present, because otherwise, in all cases, the plasma is overall neutral. So there must be as many ions, as many like the electrons. But the point is that, of course, due to the much greater inertia, we just don't consider them. So what is the particles, for the very same reason I reminded you so many times, essentially what is, because of the favorable ratio between charge, electric charge and mass, what is going to be significantly accelerating and so correspondingly affecting the electromagnetic field are electrons and not ions. So you can imagine that the only thing we can begin with is just write down the 4 Maxwell equations in the Gaussian system, and that's indeed what we've already seen many times. Here, just a reminder, ρ is the charge density and J is the current density. So we are in the vacuum, but in the vacuum filled with plasma. So ρ and J essentially, okay, we will see in a moment what they are. In this passage here, I exploited what I already proved you several classes ago when we were talking about electromagnetism. So essentially, I proved you that in the presence of a plane wave, working out the curl, like in this case in the Faraday's law, is equivalent to a vector product with k is the wave vector. Okay, so the direction of propagation. So ik vector e, and while the time derivative, the partial time derivative, so the rate of change of b, is equivalent to, if you look at here, is equivalent to gaining a factor of I omega. Well, minus I omega, and that it is here. So I just rewrote simply the 4 Maxwell equations just by exploiting this. So again, here the curl of B is just ik vector B, as well as here, instead of the rate of change of electric field, just minus I omega E, just like that. So I'm not going to spend too much time on this because this is something that we've already seen. Now, let's study the effect of this wave on the motion of a generic electron. So I just used just a second law of dynamics. We are not considering relativistic electrons, otherwise I couldn't use this. In particular, we will considering either steady electrons or electrons moving with an initial velocity which is perpendicular to the line of to the propagation direction of the wave. So clearly we have to consider both well, the Coulomb force as well as the Lorentz force, but as I just told you, the electrons we are dealing with are non-relativistic. So essentially this factor V over C Well, E and B have the same magnitude. V over C is negligible, so essentially you can neglect the Lorentz force. So we just care about the effect of the electric field. So this is the equation. I just divided by the mass of the electron. Here, minus stands for the fact that I implicitly assume E, so the electron's charge as a positive quantity. So I have to account for the negative charge by hand. So by introduces this minus sign. So, well, this equation can be easily integrated, and that's the integral, that's the result. So the velocity of the electron is a function of time. It's straightforward to see that this is indeed the case. Well, you can just derive with respect to time this equation. It's not so straightforward as it might look, in the sense that, okay, this is just, once you prove this, of course, this is just the electric field, so you can just write E. So the temporal dependence is encoded within the electric field. What I was saying is the fact that, indeed, if you derive this formula here, in particular this term, which is the only one which varies as a function of time, you should, in principle, given that you are calculating the total derivative of the electron, of the velocity of the electron, you should also calculate the time derivative of the vector position, of the position vector r. So not just this term, which is apparently here and which is apparently responsible for minus I over omega, which then fade away. But in principle, you should also consider this guy here. But as a matter of fact, this is not r. This is the scalar product between k and r. So if you either assume that initially the electron is not moving, or that it's moving in a perpendicular direction with respect to k, it means that this scalar product is constant, because this scalar product is nothing but k times the parallel component of the position vector of the electrons. But if the position is the electron is moving perpendicularly to k, it means that this guy is not going to change. So this quantity here is constant under these assumptions. If you remove this assumption, so if you just drop this assumption, then you have to consider, in the most general case, that this term gives you an extra factor and a contribution in the time derivative. So this is just for to be precise. You see, now you know exactly how the electrons move. I just speak in I assume plural. We can consider as many electrons as we want under the same assumptions, of course. So essentially, you see that you know the velocity of the electron. In particular, you also know the dependence on time, which is, as I said, encoded by E. And automatically you can, as soon as you assume a number density of electrons, so number of electrons per unit volume, which is exactly this quantity here, which I call n. So n is a number density, so how many electrons per unit volume. So you see that you remember very well the current density, J, is the charge density, which is minus En. Why? Because I have the number of electrons per unit volume times minus E, which is the electric charge of each. So this guy here, minus En, is the charge density of the electrons. I'm just talking about the electrons, times V. Density times velocity is the flux density. Okay, we've seen in so many different fashions. So indeed, this is the current density due to the electrons which respond to the electric field of the wave. But you see, if I replace V with what we found here, so minus IE over m omega in E, essentially what I end up with is a relation between the electric field and the resulting current density, resulting because J, in this case, is the consequence of E. I apply to my generic plasma a vector field, an electric field E, and as a consequence, the plasma responds with this current density. So I can define the so-called plasma conductivity, because indeed, the conductivity, as you know, is something which tells you for a generic medium, whenever you apply an electric field to that medium, the medium responds with the current density. So with the current, particularly the current density is, so sigma, the plasma conductivity is the relation, the proportionality constant between the electric field applied to a generic medium and the resulting current density. As seen in this way, you can look at this from a different fashion, in the sense that now you can consider the plasma as it were a medium with its own properties. So in particular, in this case, with this conductivity. You shouldn't be confused by the fact that this conductivity is an imaginary quantity. The imaginary quantity is just telling you that essentially there is a phase shift between the electric field and, in this case, the current. Okay, in particular, there's a 90 degrees shift, as you remember. So this is just the meaning of this quantity. But you will see in a moment that looking at the resulting equation, Maxwell equations, in this way, it's very handy, it's very powerful. Of course, charge is conserved, so the charge conservation is expressed through the corresponding continuity conservation, where ρ is inevitably the charge density associated with the electrons. And so given that there is a temporal dependence of the electric field, of the velocity, of the current density, it's also immediate to show that also ρ can depend as a solution of this equation, can depend on the same way. So it means that when you calculate the rate of change of ρ, again, you gain an extra factor of minus I omega, which is indeed what I did when moving from here to here. And as well, of course, because of the same dependence on time of the current density as the electric field, the divergence is equivalent to the scalar product with K. So, in an equivalent way, you can also define a charge density, which I remind you, this charge density is associated with J. J is the current density associated with the electrons. So ρ refers to the very same electrons. So in this case, I call a perturbed charge. So is the current density, is the charge density which is associated to the electrons which respond to the electric field of the electromagnetic wave. So this is just straightforward to show that you just replace J as the sigma. So sigma E is sigma K scalar A over omega. So it's very simple mathematics. Now, we define, given that we are now looking at this plasma in vacuum as it were a medium with its own properties, we conveniently define a so-called dielectric constant. We will see in a moment why it is defined, as I'm going to show you. So we call this epsilon, which by definition is 1 minus 4 pi sigma, so the conductivity over I omega. So pretty dodgy, weird thing, but it's going to be no more weird in a moment. It's interesting to replace the value for the conductivity, so which is this guy here. So I just replaced that. I didn't do anything else. So I go away. They vanish, and so 4 pi n is square over m omega square. You see, this has to be dimensionless. This ratio has to be dimensionless because it has to be homogeneous with I. So first of all, you see that indeed the dielectric constant is something dimensionless. And given that here in the denominator you have omega square, so frequency square, it means that all this guy here, so 4 pi n e square over m, has also to be a frequency square. I define this guy as omega p. So omega p is the square root of all this stuff. So 4 pi n e squared over m, where I remind you E is the electron's charge and m is its mass. So if you change, if you consider different particles, of course, the plasma frequency changes as a consequence. But you see that essentially these are all constant as soon as you fix, as soon as the particles of interest are electrons, and indeed they are, as a matter of fact, in all contexts, for the reason that I just told you at the beginning of this class. So the only variable which may vary depending on which context we are considering is the number density, n. So this is very, very important quantity which defines the property of the plasma. So in particular, the capability of the plasma in responding to the crossing of a given electromagnetic wave in a moment that we will see. So it just depends, and it scales with the square root of the number density. So the more dense the plasma, and the correspondingly, well, with the square root, according to the fashion, to the square root fashion, the correspondingly higher the plasma frequency is. Just a note, just an aside note, I keep calling omega as frequency. You know very well this is angular frequency or pulsation. The true frequency is omega over 2 pi. Just here it's more practical to call it frequency otherwise. Okay, and this is very important, and I would like you to remember this for the reasons that we are going to see in a moment. So this is just a summary of what we've come up with. So both the formula for the charge density, so the perturbed charge density, so the charge density associated with the electrons which are moving, and the dielectric constant epsilon defined this way, and that we also found that can be also defined as a function of omega and the omega plasma, so the plasma frequency. Now let's get back to the Maxwell equations we began with. So these are just copied. I just copied what we obtained in the couple of slides ago, and in which, as I see, I replaced the curl and time derivative with the corresponding operations. Now, if you look at in the light of the new quantities that we defined, in particular, let's focus on the first one. You see, the first one, I just replaced, instead of rho, the charge density of the electron. So what I implicitly doing here, I'm considering the contribution, how the resulting wave is affected by the charge, by the current density of electrons. So electrons become active. So they are also responsible for the electric field and the magnetic field. In particular, this is done by replacing the corresponding charge density that we got here into here. So here, if you just see 4 pi sigma over omega, k scalar E, and I just brought this guy here on the left-hand side of the equation. So k scalar E is collected here. And then given that I also collected I have to divide by I as well. Otherwise, I just replaced, instead of rho, this value here. Then, if you pay attention to what is inside, what lies inside brackets, you immediately recognize this guy, which is epsilon. So this is indeed ik scalar epsilon E, which has to be 0. This is just the Maxwell equation. And if you pay attention, now let's focus on the fourth equation, so on Ampere's law. Again, you see here J, instead of J, I just put sigma E, so the conductivity times E. But now, you see that if you arrange terms, in particular, you collect minus I omega C, minus I omega over C, you have E, and then if you divide by omega and by I, you have this guy here, multiplying this first term. So you can collect this guy, and minus I omega c time E times what? Well, times 1 minus 4 pi sigma over I omega. But that's indeed epsilon. So indeed, here you have epsilon E. Very easy. Why is this convenient? Well, if you look at now at the four equations, these four equations are the equations that are Maxwell equations that you write in the absence of charges and currents, but within a medium, no more in vacuum. So we turned the problem of charges, so of the electrons, in vacuum into our source-free, so no more charges, no more electrons, nothing, but no more in vacuum, in a medium. We changed the description of we look at now at the very same equations from a different point of view. So instead of, as I say it again, instead of charges and currents due to our electrons in vacuum, now we look at the same problem. We turn the problem into a source-free, so no more charges, nothing, but the medium is no more vacuum. It's a medium with a dielectric constant epsilon. And if you look at here, possibly, you know that we are no more in vacuum and you are in medium, you have to add in the Gaussian system an epsilon, which is the dielectric constant. And well, this just remains the same. And instead here, you have in the Ampere's law, you have that instead of E becomes epsilon E. So it is exactly what we've come up with here. Why is this useful? Well, we'll see in a moment, but essentially you can immediately appreciate that if you take the third law, Faraday's law, for example, and you multiply with vector product ik vector this guy here. So this is equivalent to multiplying ik vector this guy here. Okay, so I just took the coefficient I omega over c, just put it first, and then this guy here. But k vector b, now I'm exploiting Ampere's law, so the fourth law, which is just this guy here. So instead of KB, ik vector b, sorry, I just put here minus I omega over c epsilon e, this guy here. And so now let's develop. Now, first of all, let's compare this term here and this term here, which have to be equal, of course. You have I squared in both terms, so just ignore i's. And then here you have a double vector product. So by now you heard me exploiting this so many times. So let's do it once more. So the first scalar of the third times the second. So k scalar e times k minus the first scalar of the second times the third. So k scalar k squared times the third e. We immediately know that this guy is 0 because the electric field is perpendicular to the direction of propagation. So this scalar product is 0. And well, this guy is just omega squared over c squared epsilon e, just like that. Minus because there's minus here. So indeed, you are left with this equation. Of course, you have the same vector. So essentially, the equation becomes a scalar equation between, so k squared equal omega squared over c squared epsilon, which is indeed a dispersion relation, if you remember. So the relation between connecting the wave number k, so which has the information about the spatial periodicity, and omega, the pulsation, which encodes the information about the temporal periodicity, is just this is the so-called dispersion relation, which you see, given that we turn the problem into a problem with a medium, which is no more vacuum, you have an epsilon, which includes the information about the properties of the medium. So this is the dispersion relation as long as epsilon depends on omega. But if you look here up on the right, you immediately see that indeed epsilon, so the dielectric constant depends. It does depend on omega. So it means that the medium is dispersive, because if you remember, omega over k is the so-called phase velocity of a wave. The phase velocity is, in the case of a of a simple planar wave, is also the propagation velocity. But okay, then I'll make a comment later on. So you can also define the corresponding refractive index. If you remember that the refractive index is defined such that c, the speed of light, over the refractive index is indeed the phase velocity within that medium. So this means that the refractive index is the square root of epsilon, which is, so replacing, using the definition of epsilon, so the result we obtained about epsilon, so we immediately see that essentially the plasma behaves like a medium, like a dispersive medium, and whose refractive index, which I call NR, and R stands for refractive, of course, is the square root of the sky. You immediately see that in order for the refractive index to be a real quantity, there is a limit. There's a constraint on omega. You cannot think of any possible, if you want, well, I should say it this way, if you want all the solution to be valid, so in particular that the wave propagates through the plasma, of course this guy has to be real. Otherwise the solution that we've come up with doesn't hold. That has no solution. So it means that you do not have an electromagnetic wave which keeps oscillating while propagating through the plasma. So in order to have a wave, an electromagnetic wave which propagates through a region with plasma, omega, in order this guy to be real, to be positive, so the argument of the square root, it means that omega has to be greater than the plasma frequency. So this is immediately something which is very important, and I will comment again in a moment. So, okay, rearranging terms here from the dispersion relation, you see that you multiply this guy here and this guy here. And epsilon omega square, well, it's just for kids. If you multiply by omega square, you see that this is just omega minus omega p square. And okay, here it's just copied the very same. So the definition on one side of plasma frequency as well as the relation we just obtained. So k square, c square, this difference here. The comment I was mentioning before is indeed that we immediately appreciate the meaning of the plasma frequency. So if you have a wave with a given omega just entering a region with a plasma, so with an associated plasma frequency, the wave will go through only if the frequency is higher than is greater than the plasma frequency. So the plasma frequency, otherwise you have a, which you know, the oscillatory solution becomes a negative exponential. So you have a decrease comparable with this length scale that you see here. So essentially the plasma doesn't let the wave through. So the plasma frequency works like a high-pass filter in a sense. Everything all the electromagnetic waves whose frequency is below the plasma frequency are not going to through. They're just either reflected or absorbed, depending. They can also be reflected. I'll make a few examples in a moment. So this is very important. So that's why the plasma frequency is something to bear in mind. And so let's call the true frequency. So omega p over 2 pi, which is indeed the one you measure in hertz. So you see, the comment I was mentioning when I first introduced the plasma frequency is that as soon as you consider electrons, all these guys here, all the quantities, these quantities are constant except for the number density. So you can just calculate in particular. Okay, this is just the result of this guy, of the new p. So all these are constant except for square root of n. So it's useful to calculate once for all. And this number here, so square root of e squared over pi m, I advise you to calculate, is, oh yes, this is a good point that I wanted to make. For example, this is a very easy question that I could ask you during an exam. Oh, do you remember what is the plasma frequency? So you introduce, you say, okay, the plasma frequency is the frequency at which, below which waves cannot propagate through a plasma. This is the formula, and this is important, so I would like you to remember this. And so I could ask you to calculate. So to calculate this, it means that you have to remember the electrons charge in the Gaussian frame, as well as is in the Gaussian unit, and also the mass. Yes, this is important because we are talking about electrons, mass, and charge, so physicists should know that. So it takes little effort if you're not familiar with the electron charge in the Gaussian system, but it's worth doing once for all. You immediately see, so people who can do that, you can immediately estimate that this factor is close to 10, so more exactly, very close to 9. So 9, 10, square root of n in units of kilohertz, where n is meant to be in particle per cubic centimeter. So this is very, very useful. So I just remember, for example, 10 times square root of n, and the result is in kilohertz. So as soon as you consider different environments for which you know the number density in particle per cubic centimeter, you immediately calculate the plasma frequency. So you're immediately telling you, oh, this frequency that I'm thinking of is going through, no, is going to be stopped, or either stopped or either reflected or absorbed. So essentially, what is the plasma frequency what's the meaning essentially? Well, the plasma frequency tells you the capability, the ability of the plasma, of the electrons in the plasma, to respond to the electric field of the wave. So if the wave is sufficiently, has a frequency which is sufficiently high, it means that the plasma cannot cannot rearrange in order to cancel the effect of the, you know very well, when you apply electric field to some medium, charges tend to rearrange in order to counterbalance the electric field. Well, if you have a wave, so an oscillating electric field, of course, if the electric field is oscillating too fast, the electrons just keep oscillating as a consequence. So you have the propagation of the wave. But if the electric field is oscillating is oscillating relatively slowly, so the frequency, the associated frequency of the electromagnetic wave is low, it means that the plasma is fast enough to arrange and to counterbalance, let me say. So the wave essentially doesn't propagate through the plasma. So that's from the descriptive point of view, the meaning of the plasma frequency. Okay, so this is something useful. So it's useful also to be able to calculate on the fly. That's why this is done. So let's make a few examples. Well, the first example one can think of is the ionosphere, the Earth ionosphere, which goes from several tens kilometers all the way up to several hundreds kilometers. And so the density is varying, but at some point, some levels have a number density of 10 to 4 particles. Well, this should be several hundred kilometers away above, but so on the order of 10 to 4 particles per square centimeter. So you immediately see you have 10 here times 10 to 2 because the square root, so 10 to 3 kilohertz, so of the order of 1 megahertz. So what does this mean? Well, it means that if you are hoping to study the universe, so to study, for example, radio waves produced by a source, whose frequency, and you are interested at frequencies which lie well below 1 megahertz, there's no way you can. The only way is to build a radio telescope above the atmosphere, or to build it somewhere else on the moon or whatever. But because the ionosphere will not let frequencies of this range through. You see, while at much higher frequency, essentially the ionosphere is transparent. Because, for example, if you study the universe at 1 gigahertz, you are orders of magnitude above the plasma frequency, the corresponding plasma frequency. So it means that essentially wave can propagate. So you see immediately that the plasma frequency associated with the ionosphere is really important to understand. I was talking about the dispersive properties of plasma. And by the way, an aside comment, now you see why it is so important to understand the basics of waves, something that many of you learned for the first time with myself. So in particular, the dispersion relation, it means that if you consider monochromatic waves of different frequency, they propagate through the plasma with different phase velocities. So, the way this happens is just encoded by the dispersion relation, which tells you omega is a function of k. Now, let's work out the so-called velocity group velocity. The group velocity, unlike the phase velocity, is telling you when you have a packet, a temporal finite signal. Because if you think a monochromatic wave is an ideal solution, which has an infinite duration. But as a matter of fact, in all real context, when you have an electromagnetic wave, it's a wave packet. So it's something which is temporally finite. And because of Fourier analysis, you know very well that in order to have a temporally finite signal, you have to sum up many monochromatic waves, and the resulting velocity at which they propagate this packet, this wave, electromagnetic wave packet, is given by the group velocity, not by the phase velocity. And the two are equal only for non-dispersive media. So let's see all the stuff applied here. The only thing one needs to know is to remember that the group velocity is d omega over dk. So we want to calculate now d omega over dk. Here it's easier to calculate the reciprocal. Then we just swap the denominator and numerator. So dk over d omega. Let's have a look here. So k is square root of this guy and 1 over c. So indeed, here I just wrote what ke is as a function of omega, so square root of this guy here over c, just like that. Now, this is just for kids. If you work out the derivative with respect to omega, you see that this becomes 1 over omega, 1 over square root. There is a 1 over 2 at the denominator, and here the denominator you have 2 omega, so 2 cancels out. So omega over square root. But omega over square root is, if you think, epsilon is omega minus omega squared. So this guy here is at the denominator 1 over square root of omega squared minus omega squared p. You divide both numerator and denominator by omega, so you end up with 1 over square root of 1 minus omega p over omega all squared, which is indeed square root of epsilon, just like that. So also from a dimensional point of view, you see that this should be dimensional. From a dimensional point of view, this is the reciprocal of velocity, and indeed this is a reciprocal of velocity. So it means that, okay, the square root of the dielectric constant is also the refractive index, which we called NR. So the group velocity is the reciprocal, which I call Vg, is the reciprocal, so is d omega over dk, so CNR. You immediately see that NR is the square root of epsilon. This is something you know, and epsilon, this is guy here. So the refractive index is the square root of. Now, a comment that I didn't make before, but now I'm going to do now. You see that the refractive index is lower than 1. So if you get back to now getting back for a moment to the previous slide here, you see that the phase velocity, omega over k, is c over n. N is something smaller than 1. So c over something smaller than 1, it means that this is larger than c. So this should have kind of you could worry about this. Oh, how can it be that the phase velocity of a monochromatic wave is higher than the speed of light? Yeah, is this a contradiction with relativity? No, because essentially information travels through wave packets. Doesn't travel with you receive information when you receive a modulation of a wave, not with just a monochromatic wave. You have no information. So the information is carried forward by the group velocity, and indeed the group velocity is smaller than the speed of light. So you see, this is very important to note. So not only here, there are a few comments to make. I'm just summarizing them. So the velocity, the group velocity, is the velocity at which is actually the information and carried by the packets of electromagnetic waves just propagate, is below c. So indeed, the information travels at a speed which is below the speed of light. And also, you also see that the group velocity indeed does depend on the frequency. So it means that indeed the medium is dispersive. So if you have a narrow packet, you have an impulse of electromagnetic radiation. To have this impulse, it means that you have the contribution of many different frequencies within a frequency range, okay? And the frequency range from the duality, because of the duality between the frequency and time space, the narrower the peak and the broader the frequency range that you need to consider to make a narrow pulse. So it means that let's suppose given at some point a source of electromagnetic wave gives a pulse with a given duration, and this pulse then propagates, has to cross a region where there is some plasma. You immediately see that the result of this packet coming out of this plasma will be dispersion. So it means that you see which are the waves which are traveling faster. Well, the smaller the term, the higher the velocity. So it means that the smaller the term is when the higher the frequency. So the higher the frequency, the faster the wave. So it means that out of this plasma region, you will see first coming out the frequencies, the highest frequencies, and then correspondingly the lower one. So the pulse will be dispersed. The overall temporal profile of this pulse will be stretched. You don't have any more a narrow pulse. You will have a kind of broader pulse, which the broadening is due to the dispersion, because now first higher frequency come first, and lower frequencies lag behind. Lag is like the jet lag, In Italian is lag behind it. Seguono con ritardo. Okay, this is just a figure, nice figure, which shows you, depending on the frequency range, what happens in the different. Here there are different layers of the ionosphere. I'm not an expert on that, so depending on the layer, they have their own names. So these are the names of the layers. You see, when the frequency is very high, so sufficiently high, so higher than the plasma frequency associated with the different layers of the ionosphere, the frequency gets, so the wave gets through. And so you can also, this is also interesting from another point of view, and this is the meaning of this drawing, is that, and this was also the lack of Guglielmo Marconi. He was not aware of the presence of the ionosphere in the late 19th century, the beginning of the 20th century. But lucky him, the ionosphere had a plasma frequency which is higher than the frequency that he used to generate waves. So because of this, these frequencies are not cannot go through, but are reflected, which is indeed what you need to make these 2 points on the Earth's surface, which cannot be connected in a straight way because of the curvature of the Earth. They can be in touch thanks to the reflection of the waves due to the ionosphere. So you see that this effect can work provided that you are much below the plasma frequency associated with the ionosphere. So this is kind of a luck that Marconi benefited from. So, okay, so depending on your goal, you can exploit, you want to be able to get through or just to be reflected. Let's get back to the astrophysical context. Even if you see, this is very general physics. Again, I want to remark that the essence of this course. We see things which are very relevant in many astrophysical contexts, but essentially the physics that we study is very general. So that's also useful for many different applications and many different contexts. So we've seen that indeed the plasma behaves like a dispersive medium. Here is the group velocity. And indeed, in many astrophysical contexts, the density is so slow so that the corresponding plasma frequency is few kilohertz. In many, this is something that I already told you, in many contexts, the plasma density is of the order of few particles per cubic centimeter, 10, 100 when it is large. So you see 10 square root of n means 10 square root of something. So 10 kilohertz or even less. So in the radio band, in typical observations, in the radio band in which observations are carried out, so this means frequencies of at least of the order of several hundred megahertz. So it means that you are orders of magnitude above the corresponding plasma frequency due to the interstellar or intergalactic plasma. And it means that this ratio here, omega over omega p, is a very small number, because here this is just a few kilohertz and this is just at least several hundred megahertz. So it means that the deviation of the group velocity from the speed of light in vacuum is very small but important. And we will see in a moment why. Because as a matter of fact, from a mathematical point of view, it means that the square root of 1 minus something small can be Taylor expanded. And you know very well, this is something for kids. Square root of -1 minus something small is just 1 minus 1/2 that something small. Here I replaced, instead of the omegas, just the nus. Well, just 2 pi, both, they just cancel out. Why is this useful? Well, I just told you that the effect of this dispersion is that higher frequency just come first and lower frequency lag behind. Let's calculate the delay, the temporal delay. In particular, let's assume that at some point at t equals 0, a pulsar, which is a typical neutron star, which is capable of emitting radio waves, which is at a distance L from us, okay? And this, at some point at t equals 0, this neutron star emits a pulse, a radio pulse. So we calculate the so-called TA, which is the arrival time of this pulse to Earth. Well, how can I do that? Well, you know the distance, L. You know the velocity, which is traveled by this pulse, which is the group velocity. So you have to consider that along the line of sight traveled by the wave, density can vary. And so the plasma density can vary. And so the group velocity changes. Why? Because correspondingly the corresponding plasma frequency changes. So in principle, you have to calculate the time it takes for a source to travel for something, in this case the wave, which travel the path with a variable velocity. So you cannot just calculate distance over velocity, but you have to calculate the integral. The integral of what? Of the infinitesimal displacement, of the small displacement L dl over the instantaneous velocity, dg. But apart from that, this is really for kids. I mean, if you take one student of the first undergraduate year, you can immediately write this down. Integrated from 0 to L, from the source to Earth. Now, this guy here is c times 1 minus something small, but again, you know very well, Taylor expansion, 1 over 1 minus something small is equivalent to 1 plus that something small. So it's equivalent to multiply 1 plus this guy here. And, well, the first term is integral of dl over c is just L over c. And the second one, you see, well, nu doesn't depend on the line on the path along the travel. They're all constant except for nu p. In particular, if you explicitly write what nu p square is, and is pi d square over mc, over m, sorry, you immediately see that the only thing that cannot be taken out of the integral is n. Okay, so you can take all the remaining parts out because they are all constant, or like in the case of frequency, it doesn't depend on the point along which you integrate. So the only possible thing that can depend, indeed, if you cross different regions with different number densities, this cannot be taken out. So you have to leave it as it is. But what is important here is that you see, if you consider the arrival time as a function of frequency, you see that, so considering different waves of different frequencies, you see that this guy is the same for all, of course. This integral is the same. It doesn't change if you consider different frequencies. But the only terms is here. In particular, there's a 1 over nu square dependence. So again, all this second term, the higher the frequency, the smaller this term. So indeed, we see that higher frequency comes first, but now we can measure the relative delay. So in particular, if I call delta TA, the delay in the arrival time of a generic wave with frequency nu, with respect to what? With respect to the case in which the frequency is infinite. It's an idealized case, of course. So let's consider an arbitrarily large frequency nu. In that case, of course, this term vanishes because nu is arbitrarily large. So in that case, the arrival time is just L over C. So instead, if you consider generic nu, so you have the arrival time minus this guy here, which is the arrival time for an infinite frequency, is just this guy here, where d with d, okay, this is so the arrival time delay, so the delay with which a generic frequency omega nu arrive with respect to the infinite frequency case, where d is something which by definition, is the integral of the number density integrated along the path traveled from the source to the observer by the wave. This d, capital D, is an extremely important quantity, which is also the title of the slide, which is abbreviated as dm, and it is called dispersion measure. You immediately see that as soon as you have no plasma crossed by the wave, d is 0. And so the more plasma it is crossed by the line of sight, the correspondingly larger will be d, and so the correspondingly longer will be the delay. So the dispersion measure is indeed a measure of how a narrow pulse is dispersed due to the plasma. So you indeed see that one of the first major effects of the plasma on the electromagnetic wave propagation. So the signal gets dispersed, and depending on frequency, the dependence is 1 over nu square. So this is a kind of a signature. If you can manage to measure the relative delay between waves associated with the same pulse, but seen at different frequencies, and if you measure the delta TA, so the arrival, the delay in the arrival time as a function of frequency, and you see indeed this scaling, you see that this delta TA scales as 1 over nu square. Well, this is a really strong signature for plasma dispersion. And you immediately see that if you measure this guy, and of course you know the frequencies at which you are measuring, you immediately measure d. So you can weigh, you can measure, you can constrain the amount of plasma that has been crossed by the wave along the path traveled by the wave. What you need is a source of electromagnetic wave which is capable of emitting relatively short pulses, because you need something which is narrow, which lasts for a moment. In that case, you can measure delta TA. Otherwise, if the source is constant, how can I measure delays between the signals which are constant in time? And indeed, nature has provided us with plenty of these sources. Pulsars indeed behave like this. So again, you see that you have all quantities here, and you can replace again all these electrons charge in the mass, the speed of light. So the only quantities that can vary depending on the dispersion measure as well as on frequency are just these two here. So that's why I express this way. So if you work out this quantities here, the result here of the delay is expressed in seconds. S as a function of S means not as a function of variable, it means just the units, the units of measure, seconds. Provided that you measure, well, the frequency in hertz, and D, you see, well, let's have a look at the dimensions of D. D is N is 1 over volume, particle number over volume, so is centimeter 1 over a centimeter cube. You integrate over length, so in principle should be 1 over a centimeter squared, so centimeter to -2. But as a matter of fact, in astrophysics, the line of sight, you see that the integral is from the source to the Earth. So these, as a matter of fact, is very long distances. And you know very well that distances in astrophysics are measured in parsec or kiloparsec, megaparsec, gigaparsec. So it's a common practice to express D instead of 1 over length square as the leaving N in centimeter to -3 times parsec. So D has to be expressed in units of parsec time centimeter to minus cube. So if you do that, then you can exploit this formula here, and you immediately have the delay in seconds between the frequency, the generic frequency, and the infinite frequency. So this is an example of what you observe in the case of the Crab Nebula, our old friend that we used so many times, because it's a powerful source also in the radio band. So you see here, let's have a look at this plot, the meaning of this plot. Here on the y-axis, you have the frequency at which you are observing. This is in megahertz. So you see, these are the values. And on the x-axis, you have time. So if you look at this pulse, this is if you look through an horizontal line, it means you fix the frequency and you see the signal as a function of time. You can do this for many different frequencies. Okay, so let's have a look at here, 435 megahertz. So you see nothing, and then boop, you see this pulse, and this pulse is at this time. If you play the same game with a lower frequency, you see that the arrival time of the pulse is later. And you clearly see that the later, the lower the frequency, and the correspondingly later the pulse. So what you measure, if you are integrating the signal across this bandwidth, so you see signal lasting all from here to here. So what you measure is the black signal here. So you say, oh, there's a long pulse. Well, indeed, the pulse lasts quite several tens of milliseconds if you look at them. But indeed, this has nothing to do with the signal, with the pulse emitted by the crab. All this is the result of the plasma, both surrounding the source, but mainly across the interstellar plasma. So all the plasma that lies between crab and the solar system. And if you correct, so again, the dependence is 1 over u squared. Here the range is narrow, is a narrow frequency range. So you don't appreciate the curvature. I have other plots showing that. But here, the scaling with frequency is exactly 1 over nu squared, which is exactly, as I was telling you, the signature of the plasma. So this is the black one is the so-called dispersed pulse. So dispersed by what? By the plasma lying along the line of sight from us to crab. If you correct, because now you know, once you measure the plasma, you measure the dispersion, measure D, you can correct. You can correct and reconstruct what the original pulse was. So you obtain what it is called as the dispersed pulse. So the pulse observed corrected by the effect of dispersion due to the plasma. And what you come up with in this case is the red line here, you see? So this is the original pulse emitted by the crab. So very narrow, very short. So in the absence of the plasma lying along the line of sight, you would have observed this. But because of the plasma, it has nothing to do with the crab. It's just lying on the line of sight. What you observe is this. So you immediately see that if you are not aware of this, if you do not correct that, you might infer properties, something which are completely unrelated to the source. Okay, so this is very, very important. And you see that the lower the frequency and the stronger the effect because of the 1 over nu squared dependence. And this is all about dispersion measure. There is a second effect, which is also very important and very beautiful, which is the so-called Faraday rotation. Let's explore this in detail. So the Faraday, in order to have to do with Faraday rotation, in addition to the ingredients that we've seen so far, so region filled up with plasma, you also need another ingredient, which is an external magnetic field. So the region not only is the region filled up with plasma, permeated with plasma, but it has also to be there must also be some magnetic field within that region, something which we didn't consider so far. And in this case, you can also hear in terms of the definition of this ambient as a magnetized plasma, so or magnetoactive medium. So a plasma which lives, which is permeating a region in which there is also some magnetic field. And again, this is nothing but rare in astrophysics. I told you already that in our own galaxy, not only do you have plasma, but you also have the magnetic field, which is of the order, in this case, of a few microgauss. So the question, of course, you can understand that the presence of the magnetic field can affect, and indeed it does, the description, the solution of the way the electromagnetic fields are affected. So let's now review all this. Before doing that, let's remind ourselves that as soon as you have a magnetic field and you think of electrons, you can associate also the so-called cyclotron frequency, where omega b, again, apart from a factor of 2 pi, omega b, I remind you, is the electric charge times b, 0. And so this is also, again, a lot of constant speed of light, mass of the electron, charge electron. So it's useful also to replace all the values except for the only variable, which is the intensity of the magnetic field. So if you replace that, you immediately see that when B0 is meant to be in units in Gauss, you have something of the order of a few megahertz as cyclotron frequency. We will see why it's useful to have this in mind. What I'm going to prove today, and possibly I will finish on Friday, and immediately I'm foretelling you the result of the effect of the presence of the magnetic field, is that if you consider a linearly polarized wave just coming in, this is the region filled up with plasma, and you also have a magnetic field. In particular, what we will see, what is relevant is the parallel component of the magnetic field, parallel to the line to the direction of propagation of the wave. So what essentially comes into play is the parallel component. So let's assume for simplicity that the external magnetic field is just parallel to the propagation. So if the incoming electromagnetic wave is linearly polarized, so the electric field, for example, is oscillating up and down this way, we will see that the result of the plasma is, well, the dispersion, that's something which takes place nevertheless, because but we will see that in addition to that, there is also another effect on linearly polarized wave, that you see that the resulting electromagnetic wave is still linearly polarized in general, but the effect is that the plane, the polarization plane, so the direction along which the electric field is oscillating, has rotated. So you clearly, this drawing, I just took it from Wikipedia, which sometimes has very beautiful figures, and this clearly illustrates the effect. So you see that the plane, the oscillation, the plane in which the electric field is oscillating just gradually rotates, and then of course when it exits, it's just fixed. So by measuring, if you can manage to measure the rotation of the electric field, and we will see that this effect also depends on the wavelength, on frequency. If you manage to measure this, you can have an handle. You can you can constrain essentially also the magnetic field, not only the plasma density. No, so let's get through something similar to what we've seen in the previous case. So again, for simplicity, let's assume this is the very same drawing. K is the wave number, is the wave vector, so the wave propagates this way, and we assume that the external magnetic field B0, not to be confused, of course, with the magnetic field of the wave, is parallel to K, okay? So, and in particular, do not get confused with what I'm going to say. What we care of will be the result on a linearly polarized way. But now, the treatment that we go through focuses on circularly polarized waves. In particular, we consider at the same time both circular polarizations, so both left and right, where plus is right and left is minus, is left. I'm not going to spend too much time on this because this is something I already spoke about with the due details when we were talking about polarization. So you know very well that indeed this description here is indeed there are the two circular polarized ways. When at the time, if you remember, we called also epsilon plus and epsilon minus, the right and left. Right, left or positive helicity, negative helicity, for the very same unfair reason that everything connected with the right hand is positive, so right-handed, and everything connected with left hand is negative. This is something I really hate as a left-handed person, but anyway, this doesn't it's not important. So, okay, so this is kind of a reminder of what we've seen in the context of polarization. And, okay, so epsilon 1 and epsilon 2 are the two directions, the two Cartesian vectors. And yes, this is something, again, a reminder of the way we define the two circular polarization modes, epsilon 1, epsilon plus, right, polarization or positive helicity, and epsilon minus, left, polarization or negative helicity. Yes, this is something I already said. So now we now want to study how the motion of the electron is affected, and we immediately see that now B0 is no more. We already know that we can neglect B due to the magnetic wave because it has the same magnitude of E, and because of V over C is negligible. But now B0 can be whatever high. So there's no assumption on the possible intensity. So this, in principle, you cannot neglect this term, this Lorentz force term, because due to an external magnetic field. Okay, so here I just exploited the fact that the external magnetic field is parallel to K. So instead of writing vector B0, its magnitude times its unit vector K. Now let's decompose the velocity of the electron on the plane, and I call V1 and V2 the two components of the velocity vector of the electrons. So the one parallel along epsilon 1 and the one parallel along epsilon 2. So for the very same reason, you immediately see, because of you immediately see that the Lorentz force B, if you work out with the right hand rule, V lies on the plane, B, so the force is just a force line on the plane. Okay, so that's why essentially the acceleration lies also lies on the plane. So the velocity, the electron will be moving again along this plane, but in a more complex way, because now you no more have only the Coulomb force, you also have the Lorentz force. So let's call V1 and V2. So V1 and V2, the two components of the velocity of the electrons, will be our unknown functions that we want to find. Okay, here I just copied both the formula for the electric field in the circular polarized waves, as well as the second law applied second Newton's law applied to the electron in this case. Let's write this explicitly by projecting it along the two directions, 1 and 2. So let's start with 1. So I just divide by m. So by definition, the derivative, time derivative, is just v1 dot. Here is dot. And then here you have, what do we have? Well, minus E over m, and then you have to take the component of the electric field along 1. So let's have a look here. Along 1, you just have this guy here. So E0 and the exponential. And then you have the second component here. You have to take, I remind you, we are projecting along direction 1. So V vector k, in order to have something along epsilon 1, you have to take as V the component along V2. In particular, V2 k, you see that you have something positive. So V2 is not, of course, the two vectors are perpendicular. So just take the V2, and then the rest is just the same, minus E B0. B0 is constant, so the external magnetic field, we assume it constant. So minus E B0 MC B2, just like that. And this is all for a component from the projection along 1. Let's do the same. Okay, here I just exploited the fact that you see the coefficient multiplying V2 is the cyclotron frequency, E B0 over MC. So it's good to write it this way. It's much handier and meaningful. So let's do the same game with along 2. So V2, now V dot, because I'm deriving, this is the rate of change of velocity projected along 2. So minus E over 2, minus E over m, because I'm divided by m. And then you have to take the component along 2 of the electric field. Let's have a look here. You see you have plus minus I times this guy. Indeed. Given that here you have minus, so minus plus minus becomes minus plus. Minus plus I, em, and then the same. The rest is just the same. Okay? What about the second one? Well, here you want to project along 2, so you need to consider V1. But V1, if you, again, right-hand rule, V1 times K, you see that you get something with a negative direction with respect to E2. So you see that the sign changes. You have to use V1, but then the sign changes. And indeed, that's why minus turns into plus. And then the rest is just the same. EB0 over MC V1, but this guy, again, is omega B. So that's what I wrote here. Let's work out the second time derivative of the first one. So I'm just considering this guy and the result here. So we now calculate the rate of change of all this guy. So V double dot, V1 double dot. If you derive this guy with respect to time, you gain an extra factor of minus E omega. So minus E omega and minus become plus, and you gain a factor, as I said, I omega. And the rest is just the same as this guy. Here, what do you have? Well, you have minus omega B and V2 dot. But V2 dot is exactly what we have at the second equation. So here among brackets, I already replaced all what V2 dot is, which is this guy here. You immediately guess that the goal, the ultimate goal, is just to end up with a differential equation with just one of the two functions. In this case, just V1. You see the goal. And now, by rearranging terms, you see you can collect all the terms multiplying the electric field. So in particular, the electric field exponential. You have a common IE over m. So IE over m E0 exponential. And here you have just an extra factor of omega. Here it is. And here you have minus, minus plus, so plus minus omega b. Here it is, plus minus omega b. And then the second term is thus minus omega b times plus omega b, so minus omega b squared v1. Easy. Now, well, I remind you, the convention is that the upper sign refers to the right polarization or positive helicity, and minus the other way. So let's make an ansatz to solve this differential equation. You immediately see that here you have an oscillatory term, and here it's a linear differential equation. So you immediately see that if you assume that V1 also oscillate with the same guy here, this is going to be a solution. What you only need to determine is the coefficient A, which I called capital A1. So now let's replace this guy into this equation, and it will give us the value for A1. So here, double time derivative. So you gain an extra factor of I omega squared, but I squared, of course, is minus 1. So minus omega squared A1, and this is just this guy. I already removed the exponential because you end up with the exponential in all of them. So you just can remove it. The second one equals what? Equal this guy here. But again, I just copied and just removed the, removed the exponential one. Apart from that, it's just the same as here. Minus omega b squared a1, because this is just v1. So v1 is this guy, and again, I removed the exponential. So this is now this is just an algebraic equation on a1. So you bring this guy on the other side, or this guy on the other side here. So this is just for kids. And you divide by this guy, you see that you end up with this guy here. You see that the omega squared minus omega b squared can be written as omega with the difference times the sum. So it can be simplified with this guy here, which is either the sum or the difference. So depending on what it is, you have in the denominator either the difference or the sum. And this immediately sets the solution for V1, because we now know A1, so we now know V1. We have to determine V2. But you see here, you don't have even to solve any differential equation anymore, because you have V2 as a function of V1 dot and this guy. So if we replace this guy here, V2 here is, you bring up the other side, on this guy on the other side, so minus V1 dot over omega b, and then this guy here, minus E over M omega b E0, exponential. V1 dot, well, something that you can calculate straight away. Okay, here I just copied. Oh, this was not supposed to show up here. Anyway, let's ignore for the time. So here I just copied the what we had before, as well as the previous results about V1. So I just replaced, instead of V1 dot, this guy here, which is just this guy with minus I omega. Minus minus become plus, so I omega over omega b, and then V1, which is this guy here, and this is just copied. So V2, so you can collect essentially, I just replaced, instead of A1, the solution we've come up with in the previous slide, so I just replaced that, nothing else. And so finally, you can collect, you see you have a lot of terms which you can collect. In particular, you have E0, the exponential, over M omega b. They are both in both terms, so you can collect them. And open bracket, here the only terms that is left over is I times minus I, which is 1, and then omega over this guy here, which is exactly this guy here, and then minus 1, because here you already considered all of them. And this also sets the solution about V2. So we now are in the position of writing the solution. Oh, yes, by the way, if you calculate this guy, you immediately see that this is omega minus omega plus minus omega b, so it becomes omega b. And omega b just cancel away, and so you're left with this guy here. You have to pay attention, plus minus becomes minus plus repeatedly. So, but apart from that, and if you compare with what A1 is, you immediately recognize this guy is indeed, except for a factor of I, is indeed A1, sorry. So this is nothing but plus minus A1 exponential. So summarizing the solution, the general solution of V, you can see that V1 and V2 are just, in both cases, there is a A1 term. So A1 exponential can be collected, and you end up with the combination, which are indeed epsilon plus and epsilon minus, if you remember. So if you want to imagine the solution, it means very simply that also the velocity vector is rotating. Okay, is also rotating. And in particular, so the velocity, by replacing the value of A1, which is this guy here, can be explicitly written the dependence on the electric field of the wave, and also on the cyclotron frequency associated with the external magnetic field. Yes, here I just instead of the this guy here is nothing but the electric field. So the temporal dependence now is encoded in the electric field E of the wave. The very same game that we did when we were considering the case of the absence of magnetic field. Now we know that, you see, the very same line of reasoning. Now we have the velocity of the electron as a function of the electric field of the wave. So we can correspondingly calculate the resulting current density through the very same equation. But as replacing the velocity, you have a relation between the electric field and the resulting current density. You see that the novelty here is omega b, which is due to which reflects the presence of the external magnetic field. If you compare with the previous results, of course, we are kind of generalizing the results that we obtained before. Why? Because if you set B0 to 0, you should find again what we already found. And indeed, when the external magnetic field is 0, the corresponding cyclotron frequency is also 0. And indeed, you end up with I n E squared over m omega, which indeed the conductivity of the plasma. So you see that now we redefine the plasma conductivity in a more general case. So in a case in which not only do we have plasma, but we also have external magnetic field. So you see how the plasma conductivity is affected by the presence of the magnetic field, sorry. So again, this automatically defines the plasma conductivity, which, you see, there's something immediately that is worth noting. You see that the plasma conductivity not only depends on the quantities that I already commented in the previous case, and on the magnetic field in this case, but it also depends on the helicity of the wave. I remind you, we are considering circularly polarized waves, particularly both cases, right and left. You see that the plasma conductivity does depend also on whether you consider a right circularly polarized or a left circularly polarized wave. It behaves differently. And if you think for a moment, that's due to the asymmetry introduced by the magnetic field. Okay, so this is, I think I already exhausted my time. So I know that this is kind of mathematical, busy stuff, but this is worth to see exactly where things, where the results stem from. So unless you have uh, questions, I would stop here. And so I remind you that I